Okay. Hi, everybody. Welcome to our third seminar for XFC 2024. We have a few housekeeping things to discuss, but then we'll be getting into the simulation environment that you'll be using to train your AI agents named Kessler. A few things. We have a few more seminars after this one. There will be one on explainability in fuzzy systems given by Dr. Scott Dick from the University of Alberta. We're looking to schedule that hopefully for next week. And then we have a couple more on gradient-based methods with fuzzy systems being given by Dr. Barnabas Bede from DigiPen Institute. Those aren't scheduled yet either, but those will be in the following weeks. So we'll get those on the schedule as soon as possible, and we'll make sure everybody has those meeting links. The schedule did get flipped around a little bit, and as such, we're going to be introducing the milestones after those seminars, or at least all the final milestones. We will send out information on the first milestones, which are some pretty basic and simple things using Kessler. So after today, I'll send that out after you get an introduction to the game. The game itself, it's named Kessler after Kessler syndrome, which has to do with space debris in orbit. But it's inspired by the classic Atari game Asteroids. And we're going to go over how to actually use the game, how to create an agent to play in the game, all things like that. And the person that's going to be doing that is Mr. Zach Phillips. Who's in the meeting right now. He's also here in the tallest Cincinnati office. He's our primary developer and was one of the main developers of Kessler itself. So Zach, I'll go ahead and turn it over to you, and so we'll get started and dig into Kessler.
All right, awesome. Thank you, Tim. So yeah, we're going to be going over the basics of Kessler, how to use it, and some very rough ideas as to how you can use some of the information that exists within Kessler to create an agent. So starting off, we have just some of the general info. Obviously, this will be recorded, so you'll have access to this information later, as well as Kessler has it's pretty well commented and is a public repo that you can always go look at any time. So Tim mentioned Kessler is inspired by Fuzzy Asteroids or Asteroid Smasher, the arcade game. It's written from scratch. There's not a lot of dependencies to it. The only real dependencies, I believe, are tkinter for graphics, and then that might be it. I don't remember off the top of my head. For the most part, though, it's very stable, very lightweight, and significantly faster than the old Fuzzy Asteroids that XFC used to use. In general, you're going to be on a map like this with asteroids on it. You have a ship with a certain number of lives. You score
points. Zach,
by...
you're not sharing.
Oh my. Oh, it just didn't go through.
There you go. Looks good.
Perfect. All right. As I mentioned, yeah, inspired by Fuzzy Asteroids, much faster and much stabler. So in short, you are going to be on a map similar to this or similar size. You will be controlling a ship in this environment. It has a number of things that it can do, but the general goal is to survive as long as possible while destroying asteroids to gain score. The actual scoring criteria for the competition will be gone over in the competition presentation, but in general, hitting more asteroids results in a higher score. So you can get a little bit of a closer look here about what that play environment looks like. The keys here is ships and asteroids wrap across the edge of the screen. So if you fly across the bottom, you appear on the top side of the screen. If you fly across the left or right, you will appear there on the opposite side from that. There is functionality for teams. The plan currently is to just have 1v1 adversarial, but there is opportunities in the future for having team-based combat as well. There's also an additional graphics engine that can be used if you would like to. It's a little bit heavier and more difficult to get set up. There's details in the README for Kessler game on how to set this up, but it uses Unreal Engine 5 to display prettier graphics engine if you really wanted to, show off for that aspect. As I mentioned, Kessler is available and is public. It is open source. It can be found at this link here. Has all the associated code, examples, things like that. You can see old changes of the game. If it's something you are interested in contributing to in the future, you are welcome to. We're always looking to add new things and to increase the depth of what we can do with the game. It's also available on PyPy, so you can just pip install Kessler game to install it. The only key there is it requires Python 3.10 plus. Newer versions should work fine, but it is definitely good with 3.10. Some brief changes for any of you who are familiar with fuzzy asteroids. We're going to be going through a lot of the setup anyway, but most of the changes are going to occur in the test controller and scenario test.py that you can really see what's actually changed. Keys are asteroids now split in a predictable fashion. They're deterministic using momentum. Each parent asteroid splits into 3 child asteroids when destroyed. And then the small side asteroids disappear when they are destroyed completely. Obviously, ships can now have more than 2 teams and multiple people on each team. The other new addition for this year is mines. Ships can lay explosive mines that will detonate after a few seconds. Right now it's 3 seconds. They will destroy any asteroids within their radius and cause them to split or disappear, as well as any ships in the blast radius as well, taking 1 life from the ship. So what you'll be making for Kessler is what we call a controller. It comes from a base class in Python called Kessler controller. And the main thing that you'll need to be adjusting in this class is what is called the actions. This is a method that is going to be provided with the ship state and the game state being a picture of everything going on in the game at that time. The ship state is everything going on with your ship, and it is expecting you to return a tuple that includes thrust, turn rate, fire, and drop a mine. And these are your control actions. So what thrust do you want to apply for this frame? What turn rate do you want to apply? Are you going to shoot this frame? And are you going to drop a mine in this frame? And that will be evaluated on every single time step of the game. Currently, that is 30 hertz. And it will then deploy those actions. We're going to go through next is what all is in that game state picture. There's a lot of information here. You don't have to use all of it. You can use as much as you want or as little as you want from it. In general, the game state is going to have a set of states for every asteroid in the game, every ship in the game, every bullet, and every mine that exist. It will also inform you of the map size, the current simulation time, and the time step. Each of those individual states that we have, we're going to go through now as well. So ship states is going to be a dictionary, one for each ship that exists in the game. It will tell you if that ship is currently respawning, if it's on its respawn timer. It will tell you the position, the velocity, the speed, the heading of the ship, its mass, its radius, the ship's ID that you can use to identify different ships from one another, and what team that ship belongs to, as well as how many lives it has remaining. You also then get additional information about your own ship, which we saw from the ship state that was passed to your actions method. You will be aware of how many bullets you have remaining, how many mines you have remaining, whether or not you can fire if you're on your fire cooldown, because the firing is limited to a given rate. What your fire rate is, the thrust range, which is the maximum and minimum thrust you could possibly apply, and the turn rate range, which is the maximum and minimum turn rate you can apply, as well as your maximum speed and the drag that is being applied to your ship. For each asteroid in the game, you'll be aware of its position, its velocity, its size, which is just going to be an integer from 1 to 4 for the different types, or different sizes of asteroids, its mass, and its radius. And then for bullets, you have their position, velocity, their heading, and their mass as well. You can do a lot of stuff with that information, however you like. You can, look into density maps for asteroids. You can look in, predicting when a bullet will hit an asteroid to know when it's going to split, things like that. You don't have to use all that information, but it is all there for you for as in-depth as you want to go, or as simple as you want to go. To use Kessler, the main thing is you have to create that controller. You will have to define a scenario. You have to instantiate the game, and then you have to run it. This is all pretty similar to how fuzzy asteroids worked. So to define a scenario, we'll go through that in a minute, but you define the initial states of all the asteroids and ships, if there's any time limits, if there are ammunition limits for bullets or mines, things like that. You then instantiate the game using the game object. We also have a trainer environment object, which is a child of the game, and that is just a game that has a lot of default settings already set up for you, such as turning off graphics, running it at maximum speed, getting rid of performance tracking, things like that, to optimize the rate at which it runs, and you can use that for training with whatever learning function you want to use or learning algorithm you want to use. There's also then a score class that will, after you run the game, that will be provided to you. It sorts all the controllers into the game, all the ships and controllers in the game into teams, and collects score values for each team, such as what was the accuracy of this ship, what was the number of asteroids hit, how many lives did it lose, things like that. And you can use that to provide scoring metrics or fitness metrics for your learning algorithm. So going over how we define that scenario, there's a lot here, but you essentially just instantiate a scenario class. You can see the parameters listed out right here. Those are the name of the scenario. Some of these are optional because you can define scenarios in different ways. For example, you can manually specify all the asteroid states, so the exact positions you want every single asteroid in, or you can just list a number of asteroids and have it generate them randomly. Ship states, by default, it will just start the ships near the center of the board, but you can also specify the exact starting positions of the ships. You specify the seed that can be used for the random seeding. The game map is going to be the map size. The time limit, if there's a time limit for the scenario, and then an ammo limit multiplier. So what this is, ammo limit multiplier is essentially, given a number of asteroids in this scenario, it takes a certain number of bullets to fully destroy all of the asteroids. The ammo limit multiplier is a multiple of that. So say there's a scenario that it takes 100 bullets to destroy all the asteroids. An ammo limit multiplier means it will give you 150 bullets. If ammo limit multiplier is 1, it would require 100% accuracy to fully complete the scenario. And then also there's an optional flag if you want the scenario to end once both teams have run out of ammo. That's useful for training things like avoidance, where you don't want the scenario to end. You can turn that to off, so you can continue to see how your agent performs without ammo. So this is an example of creating a scenario. So we're naming this one test scenario. We're saying give us 10 asteroids in random positions. We set the ships to spawn at particular positions with specific angles. They have 3 lives each. They each get 3 mines. We set a map size of 1000 by 800, time limit of 60 seconds. And then the ammo limit multiplier here is 0, and this would indicate infinite ammo. And then we're going to let the simulation keep going even if the ships are out of ammo. The next thing you have to do is you have to instantiate a game. With this, you will need to create game settings. There's quite a few settings. They all have defaults that we will run through. And so this is an example of all the settings being set up. But in short, these are the fields that you will be adjusting. First one is frequency. It defaults to 30 hertz. It means your controller will be evaluated and the entire simulation will be evaluated 30 times a second. For the competition and everything, this will be run at 30 hertz. So I would recommend not changing it. Otherwise, you get slightly different performance out of your, trained agents than what they will be in the competition. Performance tracker. This is an optional thing that runs during it to track the evaluation speed of both the simulation environment and your controllers. It can be useful to keep track of, how long is one controller evaluation taking for you in various scenarios, because if that slows down too much, it will slow the entire simulation. Print on, this is just whether or not you want it to print some various aspects of the simulation. It can be useful when you're debugging and seeing what's going on. It may not always be useful when you're trying to train or go through your machine learning process. The graphics type, this is an enum. There's a couple different types in here. There is no graphics. There's TK Enter, which is the more basic graphics you saw. There's Unreal Engine. There's also custom. If you would like, you can write your own custom graphics class to use while training if there is additional information you wanted to output or to use for any sort of presentation. If you set graphics type to custom, you will have to pass it a custom graphics object, but that's getting into a little bit more advanced functionality. The last one is real-time multiplier. This will be the target speed of the simulation. It will slow down if it cannot maintain this speed. So if you set it to 20 times real time, if it can only maintain 10 times, it will get as close as it can. If you set it to 0, it will go as fast as it can possibly simulate, which is what is used to. And then you can pass a default time limit for the game that will apply to all scenarios that don't have a time limit set. And so what that looks like is here we instantiate a game settings
I'm
dictionary.
Not sure if it's just me.
In this case, we're turning on performance tracker to true. We want Unreal Engine graphics, and we want real-time multiplier of 1. The rest of our settings, we are just going to let stay at their defaults. And then we create a Kessler game object using those game settings. Yep. Hello? Am I coming through now? Let me see here.
Can someone else
All right. Am I coming through now?
Okay. Zach, can you hear me?
I can hear you. Can you hear me now?
Yep. Okay. Now we're good.
All right. Perfect. Thank you.
Sorry about that, everybody.
All right. How much did we miss here? I'll just jump back a little bit. So we have the settings dictionary, the default settings for it. Most of these you can leave at default. The main ones that you want to be looking at is you can turn the performance tracker on if you want to keep track of the speed at which your agent is running. If you're concerned about evaluation time of your agent, you can adjust prints if you want more information out of the simulation while it is running. Is the graphics type. There are various types that will be in an enum in the Kessler game repo. The main ones you'll use are no graphics, TK Enter, and Unreal Engine. The real-time multiplier, this can speed up or slow down the simulation as best it can. 0 sets it to a completely unlocked speed and go as fast as it wants. And then you can set a time limit that is blanket applied to all scenarios. So this is an example of those game settings, leaving most of the stuff at default and just setting the performance tracker to true, setting Unreal Engine graphics to be the one used here, and a real-time multiplier of 1. You then create a game using game equals Kessler game settings equals game settings. If you're creating a trainer environment, you can see the line below that's commented out. It is the exact same format, but it will override some of the settings to turn the graphics off and to speed up the simulation. The way you then run a game is you call game.run. Once you've instantiated a game object, you pass it a scenario and you pass it a list of controller objects to be used. So in this case, we're passing it 2 test controllers. And that's going to output 2 things to you. It's going to output a score class to you, and it's going to output a performance data dictionary. And that's where that perf tracker comes from. We also have a gamepad controller that you can see in this bottom line here. What this does, it's a controller that you can use at any point, and it allows you to connect a gamepad, such as an Xbox controller, to your computer and use that to play as well. And that's very useful for if you want to play against your agent to see how it's doing, or just to get a feel for what the game is like. So the way you might implement this with a training or reinforcement learning approach, this is a lot of pseudocode here, but essentially you would initialize a population, some, the game environment, some scenarios, number of generations, things like that. And then, while your stopping condition is not met, for every individual in the population, you're going to evaluate the fitness of that. Evaluating that fitness, you'll get a score. You'll then modify the population from that. And what that fitness evaluation would then look like is you create a controller by going, my controller, you individual in the population. You then go for every scenario that you have in your scenario portfolio. You'll go score equals game.run, and you pass it that scenario, you pass it that controller, and then you use that to keep track of a total score, and you can return that. One final thing with Kessler before we get into just looking at a little bit of example code is Kessler, you can customize the sprites that are in the game, and it's something we definitely encourage you to do for your agent. The way it works is in Kessler game graphics images, in your site packages, you could grab one of the existing ship sprites that's in there, and you can modify that. Or you can just create your own sprite entirely. You can then, in your controller, set that sprite path, and the game will use that to display your ship. All we ask is, make sure that any colors, text, logos, anything you use that you have permission to use, don't use any copyrighted material, anything like that. And if you send us that customized sprite, we can use it in the competition. There are some requirements for it. The main thing, it needs to be less than 20 kilobytes, which we're talking, the sprites are pretty small here. They don't need to be large. No copyrighted trademark materials unless you get permission. Nothing offensive, profane, obscene, anything like that. Try not to alter the dimensions or size of the ship sprite. Another thing to keep in mind is the aspect ratio. So try to keep it close to 1:1. Otherwise, it's going to, when it gets rescaled to actually be put in the game, it will not end up looking exactly how you intended. So if you keep the actual image 1:1, it will look how it does in the image you provide. So that's everything we have in that slideshow. Real quick, we're going to step through just a little bit of sample code to kind of get an idea of everything. So what we have put together here is we call test controller, and this is available in the Kessler game repo when you download the game. And so in your controller, you're going to inherit from Kessler controller. In the init, you can do anything in this init that you would want to. You could initialize variables to keep track of. If, say, for example, you were doing a density map of the asteroid field, you might instantiate that here. Or if you have some history-based variables, things like that for control history, you could implement that here. Anything like that you would want to use. We then have our actions method, where we get that ship state and game state, and it's expecting that return of our control values. For this real quick test, we're just setting all of our control values to 0 and false. So theoretically, our ship should do nothing. The last thing down here is you have a name property. You use this to name your ship. You can name it. We encourage you to name your agent, whether that's based on your team name or whatnot, and that will then appear in the graphics. This is then used in the scenario test here, where we create a scenario, 10 asteroids. We're only going to do one ship for now. Set a map size, time limit, ammo limit. Pretty similar to what we saw in the slideshow there. We define our game settings. So in this case, performance tracking is on. TK in our graphics, real-time multiplier of 1. We then create our game object. And then down here, we evaluate the game. And then afterwards, we're just going to print out some things from that score. And what this looks like now, if we run it, is we have the game here. And as we'd expect, our ship doesn't do anything. What we can see now is if we were to come down here to test controller, and let's give it a thrust command. And now if we play, we will see our ship is thrusting forward. We can, give it a turn command, and, maybe we'll have it shoot as well. And now we can see our ship turns and is shooting. Obviously, this is not a very good agent, but this is kind of how that control structure works. And so you can have this change every frame and control your ship from there. The other thing that we have is just to give you guys an idea of that gamepad controller. So if we now add a second ship to our scenario, and then down here we're passing our test controller and the gamepad controller. We'll see now there's a second ship, and this other ship is now controlled by me here with the gamepad. So you can use this to play against your agent if you want to get a feel for the game and how it works. Here we can see the new mine object going off. Yeah, that in short is the game. And real quick, I'm actually just to show you guys some of the printouts. So we all lost our lives, the scenarios ended, and so now we printed out some, scenario evaluation time, why the simulation stopped, because there were no ships, the asteroids hit by each team's deaths, their accuracy, and their evaluation time. And these are all parameters that you could then use when, scoring your agents during your training process. That is all I have. Obviously, there's a lot of information about Kessler. There's a lot more depth that it can go into, but the repo is public. Once again, that it's Kessler game on PyPy. And then also, if we go back here, you can pip install Kessler game as well as this github.com/talsgroup/Kessler game. That will get you to the repo in both doc strings and code examples as well that can help get you started. Does anyone have any questions?
One thing I'll add is that there will be the explainability portion of the competition as well, which will involve some more things in Kessler. We haven't fully fleshed out what we're going to do for explainability this year, but there will likely be some sort of functionality that you'll have to output some sort of explanation from your agent to. We'll do another session to give you the details on that after we've fully fleshed that out. So that'll happen after the other seminars, most likely. So for now, focus on getting comfortable with the game and playing with the controller class that Zach has been going over. Zach, one thing we've had questions about in the past was a more general framework for how to do machine learning with Kessler, so both gradient free and gradient based. So maybe if you go to your IDE again, it might be helpful for some people to kind of see, even if it's pseudocode, what you might do, because in this scenario test, what we're seeing is the instantiation of a single game run, a single game object that we're running through for a single scenario. So it might be helpful to just sort of relate this to how they might use it to train their agent.
Yeah, absolutely. Here, let me just kind of create a new Python file here just to give an idea. So just as a very brief kind of overview of what you could do is, if you are in a situation where, you've created some controller, and so we've defined our controller, so we'll just call it agent, and that's going to import from Kessler controller. You've defined some agent, and this is your agent you've created. It's going to take some sort of input, it has some level of parameters that it's instantiated from, and so its init in this case is going to be taking in, in many cases, this might even be, if you're working with a genetic algorithm, this would be called a chromosome. But whatever an individual in your machine learning population is, some encoding of how you create this controller. So we're just going to call this input encoding. And from that, you create a controller from your encoding, and it's going to have that actions method. And that actions method is going to take in the normal game state and stuff like that. But that's going to use some aspect of the encoding, some control paradigm, in this case, fuzzy logic or whatnot, to do your actions. And then, so when you actually go to run your code, you're going to go through, and the first thing you're going to do is you're going to create a population. So, we'd call some method that we'd create a population. Once we have our population, we now need to, advance through a number of generations. And so in the example of gradient free, right, we would create a population. We'll then, for generation in, say we want to do 1,000, right? Do 1,000 generations. For each generation, we would do for individual in population. And, we can do population equals that. For each individual in the population, we would want to do, individual dot evaluate fitness. And the way we're going to evaluate the fitness of an individual is, say we have a class and we're going to call it individual. And that's going to have, and however we set that up, this is going to be some level of encoding for how it works. And then we would have, create population. Or not create population, sorry, evaluate fitness here. And this would have, we'll call it self dot encoding. And that would be something, but it doesn't really matter too much what that is for now. We now have evaluate fitness. And so now to evaluate the fitness of one individual, well, jumping back down here, for each individual in the population, we want to evaluate its fitness. So we'd go through and do that, and then we would now go population dot, or we'd go modify population, and then modifying the population would be based on, we'd look at the current population, we modify it based on these fitnesses. And for, how you do that, this really comes into your learning approach. And so you might look at, for gradient free, you just look at its performance, you implement, some mutation, some crossover aspects in the case of genetic. If you're doing a gradient-based approach, your evaluate fitness now might store a gradient of fitnesses that it's estimating there, and then modify the population based on that. So this is however you're generating, this is coming from your learning approach. The key that matters here is this evaluate fitness function. It's how do we actually collect that information from Kessler. And so what that is if you have an individual here that has some level of encoding, when you go to evaluate fitness now, what you'll do is, you'll go, your controller is equal to this agent class, and you'll pass it that encoding. And so now you have a controller. And, say you have scenarios that you create here. And so, we have scenario 1. And, if we create a bunch of scenarios here that we want to use. And now we go for scenario in scenarios. The other thing that we'll need to do is we need to create a game object. So we can go game equals Kessler game. So now what we can do is we can go for each of our scenarios, we have our controller. We have a bunch of scenarios. We can go fitness equals 0 because we don't have anything for this individual quite yet. For each scenario, now we can go score equals game dot run, and we pass it a scenario and our controller. And this is now going to run each of these scenarios theoretically, but it's not doing anything with them. It's just going to loop through and it's going to run your controller against every single one, does nothing with it. But now we could go, say we want to use the number of asteroids hit as the score, right? We can do fitness plus equals score dot teams, be the first team, dot asteroids hit. Okay. And now what our fitness is here is we are adding up the asteroids we hit across all these scenarios. And maybe you want that, maybe instead of asteroids hit, you want accuracy. And we grab accuracy from that score class. And now every time it loops through and runs that, it will grab the accuracy. And a lot of this is very rough pseudocode, but this is the general idea, is that for every individual you create, when you evaluate its fitness, you create an agent, you create your controller from that encoding. You create some set of scenarios that you want to evaluate your agent over. You create a game object, and then now you loop through and you actually evaluate it across all of those. And here, if we went self.fitness equals 0, so we now just have a fitness of 0, and now we can go self.fitness equals this fitness we have in here. And now our fitness for this individual is stored. So now when we go to modify this population, we can modify it based on that fitness. Does that make sense? Any questions about like that general process? Obviously, this structure varies slightly for gradient-free versus gradient-based learning, especially in terms of how you evaluate this fitness, whether or not you are evaluating or estimating some level of gradient from that.
I'll add, in the case of doing gradient-based, where you're typically using more immediate reward, and you would likely be instantiating a number of random scenarios, as opposed to a fixed list of scenarios, like in this case. So in the case of doing reinforcement learning with gradient based methods, you would, instead of instantiating excuse me, a population of individuals that you're going to evaluate and compare, you would have one individual evaluated over different scenarios, and those scenarios would likely change depending on how you're what exactly you're doing in your reinforcement learning. But yeah, please, if anybody has any questions on Kessler, obviously, you'll probably have a few after you start playing around with it and get your hands dirty. I recommend doing that. And if you have questions after the fact, you can always contact us. Slack is the best place, as always, to ask those questions. We do typically reserve time also for help sessions. So if we have a number of questions related to similar things, we can do help sessions as needed. But please, if anybody has any questions at the moment, go for it. Zach is probably the most knowledgeable person about Kessler.
All right.
Okay. Well, if nobody has any questions at the moment, again, I recommend going to play around with Kessler, and please contact us if you do have questions. Thanks, Zach, for going over the intro to Kessler. I will be sending out updates on the next few seminars. The recordings from the previous few seminars, there was some editing that needed to be done, but they will be put up on the YouTube channel soon, definitely this week, along with this one as well. So you'll have those for reference material. All right. The YouTube channel, here, I'll put the link in the chat. You can probably find it by searching for Fuzzy Competition. That's the name of the channel at the moment. But here's the link for it. Any other questions? Looks like we may have one more. You're welcome. Yeah, I'm excited to see what you guys come up with. It should be fun. And yeah, if you happen to have a gamepad controller, just like a Xbox or other generic Windows controller, I recommend playing the game with that gamepad controller class to get a feel for it, and you can get an idea of how the game works without having to define some agent.
It's also very useful for determining what you want to prioritize when it comes to your agent, because you can kind of learn what are the difficult parts of the environment and what are the easier parts and where your focus may be.
Yeah, agreed. All right. Well, again, thanks, Zach. And I'll get this uploaded to the YouTube channel along with the other seminars, and I'll be sending out updates for the next couple seminars after we get them scheduled. Thanks for joining, everybody.
Thanks, everyone.